So far in our study of circuits, we've studied circuits that only contain resistors and batteries. So now we're going to switch our focus into circuits that contain batteries and capacitors. Much like resistor-only circuits, capacitor-only circuits can be arranged in series and in parallel, and similar to resistor-only circuits, in a series circuit, if you were making an entire loop around a circuit, you'd have to pass through all three capacitors, whereas in a parallel circuit, you'd only pass through a single capacitor in your loop. Just as with resistor-only circuits, Kirchhoff's laws still apply here, and we'll make use of Kirchhoff's laws later on in this video to derive expressions related to series and parallel circuits. In addition to series and parallel circuits, you can also have a combination circuit where some capacitors are wired in series and some capacitors are wired in parallel, much like you see in the bottom right here. Just as we do with resistor-only circuits, if we see a circuit like this, we would work to reduce the circuit by combining two or more capacitors that are just in series or just in parallel and working until we have a simple circuit. So for example, with the circuit you see here, I would start analyzing the circuit by combining C3 and C4 because those two capacitors are in parallel with each other. Next, I would combine that combination, C3 and 4, with C1 because that combination is in series with C1. And then C1, 3, and 4 would be in parallel with C2. So I would have to go through three separate steps to find what we would call the equivalent capacitance of the circuit shown here. Let's spend a little more time analyzing series and parallel circuits with capacitors. We'll start out with the series circuit, where I have three capacitors that are all connected in series, so that if I were making a loop around my circuit, my loop would have to pass through all three capacitors before making it back to the battery. We'll start off with the loop rule because, as we've learned in the past, the loop rule is one of the most important rules related to circuits. If I were making a loop around this circuit, I would start by going through the battery, and I've assigned this battery an EMF of E, and I'm going to go clockwise around my circuit. Therefore, this would be a positive EMF. When I'm thinking about a capacitor, just as I do with a resistor, I want to think about which side of my capacitor would be positive and which side would be negative. Knowing what I know about circuits, I know that we consider the current to come out of the positive side, and the current being the movement of positive charges. And so current here would come out of the battery going up this way. And if it's positive charges, that means that it would deposit itself on this side of the capacitor. So the top plate of this capacitor would be positive, and that would then repel positive charges off of this bottom plate, and so this bottom plate would become negative. Those positive charges that were repelled off of this bottom plate would then be stuck on this plate, so this plate would become positive, and this bottom one would become negative, and likewise with this bottom capacitor here. Now, of course, keeping in mind the fact that we know that technically it's negative charges that are moving in a circuit. So if I were focusing on the negative charges, they would move in this direction out of my battery and would get stuck at this bottom plate here, which would become negative. It would repel electrons off of this plate, and those would get stuck here, which would repel electrons off of this plate, and they'd be stuck on this one here. So either way, whether I'm focusing on the electrons that we know are actually moving or whether I'm focusing on the positive charges that we think of when we're thinking of current, I end up with the same configuration of positive and negative plates on my capacitor. So that when I travel around in a loop on my capacitor, I end up with that loop rule equation that you see here on the screen. I'm not quite sure why these capacitors are numbered in the way that they are, but I went ahead and stuck with the numbering that we see in the diagram. Another thing we often think about with capacitors is not just the potential difference across them, but also thinking about the charge on that capacitor. We know that charge is conserved, so it can't be created or destroyed. And if you think about that process we just went through to label each plate as positive or negative, it should hopefully make some sense that the charge on each capacitor is the same. That comes from the fact that it's these negative charges that are depositing on this bottom plate, and they're going to repel an equal amount of negative charge from this top plate, making this top plate an equal amount positive. And then that charge that was repelled off of this top plate ends up getting stuck on this plate here. So it's the same amount of charge on the bottom plate of C1 as it is on the bottom plate of C2. So on and so forth, making it true that the charge on each capacitor is the same. So we know our general equation for capacitance is that capacitance is the charge divided by the potential difference. And so I'm going to use that equation in my loop rule to come up with a general expression for equivalent capacitance in series. I started off by saying that the EMF of the battery would be like the total charge divided by that equivalent capacitance, which I'm calling C sub S. So then the potential difference across V3 would be the charge on V3 divided by C3, so on and so forth. I didn't put subscripts on the Q's since I know that they're all the same, and in the end factor out. So that my general equation says that 1 over the equivalent capacitance in series is equal to the sum of 1 over Ci. Now, be very careful because this is almost the opposite relationship that we're used to with resistors. In resistors, we find the equivalent resistance in parallel with an equation very similar to this. But with capacitors, it's in series. And that comes from the fact that the equation that we use to derive this expression here has a fraction in it. The fact that it's C equals Q over delta V, as opposed to the equation that we used with resistors. Luckily, this equation is on your equation sheet, so it's not something you need to memorize. But understanding that process that we went through to come up with this equation is important, especially the fact of applying the loop rule and knowing that the charge on each capacitor is the same. Let's take a look at capacitors that are wired in parallel to each other. Just as we mentioned before, if I am completing any loop around my circuit here, my loop, if it goes through my battery, would also only go through a single capacitor. And therefore, the EMF of the battery has to be equal to the potential difference across each of these capacitors. We also know that charge is conserved. So the total charge in my circuit has to be equal to Q1 plus Q2 plus Q3. Let's think about that. I'll focus on electrons this time, which would come out the negative side of the battery and go around the circuit in this way. If I focus on a single electron, it has an option of going up this path here and depositing itself on C1, or going up this path here and depositing itself on C2, or continuing on this path and depositing itself on C3. Every time a single electron deposits itself on the bottom plate, we would have another electron leave the top plate, travel up and around my circuit, and then depositing itself on another bottom plate. And the process keeps going until my capacitors are fully charged. Therefore, that total charge that we would have on the capacitors has to be equal to the sum of the charge on each individual capacitor once it's fully charged. Once again, we know the capacitance is charge divided by potential difference. So I am going to substitute into my charge equation that I have here. And so if I solve this capacitance equation for charge, I get that charge is capacitance times potential difference. And so I'm going to use that, plugging that into my charge equation. So my total capacitance in parallel times the EMF of the battery, that would kind of be like my total, would be equal to C1 times delta V1 plus C2 times delta V2 plus C3 times delta V3. Each of these delta V's is the exact same, so I could cancel it out to find that the equivalent capacitance in parallel is the sum of the individual capacitances. Again, this is just like how we would find the equivalent resistance in series if we had resistors only. So capacitors only circuits are kind of in reverse of series only circuits. We'll of course have lots of practice implementing this, and really that concept, the idea that charge is conserved and that the potential difference is the same across all of them, are the most important aspects of understanding capacitors in parallel.